see SIMD vectorization done on some codes from a test suite for digital signal processing. And these test codes are mentioned in one of the editions of the Hennessy-Patterson computer architecture quantitative approach book, with some interesting remarks that we will see here. Okay, so the vectorization is what is done in LMPCC, and they are done on SSA form, and other important analysis and optimizations include, obviously, data dependence analysis, constructing the loop tree. LMPCC compiler does not rely on the syntactic loops, but instead identifies loops from the control flow graph. Actually, a loop tree from the control flow graph. The reason for that is that many important loops are written with goto statements, and clearly we want to optimize everything. Okay, so other optimizations which are important to have done include SSA pre. The first case is the fear filter, which is appears to be trivial to optimize. There is nothing strange going on here. The multiplications can be done in parallel. And there is an interesting remark, namely in the Hennessy-Patterson book, that book has extremely many insights, and one of the categories is pitfalls. Why you think, or not only you, but why many people think wrong things, such as can think wrong things, expecting to get good performance from a compiler for DSPs. Okay, so, and then they remarked that for this code that we will see soon, it is 11.5 times faster to write the code in no, not to write it, but to execute it in assembler than using Texas Instruments' own compiler. Okay, and how can that be? Well, this is the code, and it's not pretty, and most compilers, or I should not say most, but many compilers give up when they see all these pointers. Okay, another example from the same benchmark suite, which becomes 9.5 times slower with TI's own compiler compared to hand-optimized assembler. And well, this is not so complicated as it might look, but this coding style confuses compilers usually.